Hello guys, welcome to another video from Computer channel. In this video, we're gonna solve the question number 16 from Sipser textbook, and this question that we're gonna solve in this session is about how to convert an NFA to equivalent DFA, and we're gonna review the theorem about this question and solve some example about this issue that we're gonna review it together. And yes, that's it. I hope you guys enjoyed this video and let's solve it together. Okay guys, as you can see here, this is the question number 16. Use the construction given in Theorem 1.39 to convert the following two non-deterministic finite automata to equivalent deterministic finite automata. First, let's take a look at Theorem 1.39. This is the theorem that we have here. Every non-deterministic finite automaton has an equivalent deterministic finite automaton. And the proof idea is that if a language is recognized by an NFA, then we must show the existence of a DFA that also recognizes it. The idea is to convert the NFA into an equivalent DFA that simulates the NFA. Recall the reader as automaton, a strategy for designing finite automata. How would you simulate the NFA if you were pretending to be a DFA? What do you need to keep track of as the input string is processed? In the example of NFAs, you keep track of the various branches of the computation by placing a finger on each state that could be active at given points in the input. You uploaded the simulation by moving, adding and removing finger according to the way the NFA operates. All you needed to keep track of was the set of states having finger on them. If k is the number of states of the NFA, it has to the power of k subset of a state. Each subset corresponds to one of the possibilities that the DFA must remember. So the DFA simulating the NFA will have 2 to the power of k states. Now we need to figure out which will be the start state and exit state of the DFA. And what will be its transition function. We can discuss this more easily after setting up some formal notation. So as you can see here, this is the proof idea that we have. We must keep track of different work that we do in NFA and somehow simulate them with an equivalence DFA. And now let's back to the question. Actually, I write them here. This is the first NFA that we have here. It has only 2 states and the transition function, as you can see here. If we are in a state number 1, if we see A, we can actually stay in this state or go to next state with this A here. And if we are in a state number 2, we can actually go to a state number 1. And if we are in a state number 1 and we see a B, we can go to a state number 2. And yes, this is the transition function that we have. Based on the theorem that we see here, the equivalent DFA must have 4 states that is equal to 2 to the power of 2 here, because the K is the number of states that we have in our NFA. So this is equal to 4, and our equivalence DFA must have 4 states. First, let's start with our start state in equivalence DFA. Actually, here we will start with 1 because we know that actually when we are 1, this is our start state in our NFA. So this is number 1 here. Yes, like this. If we see an A here, we have actually 2 options. We can stay in 1 or go to next state, that is 2. So here we have a transition function like this. Actually, if we see an A, we have to go to this state here that contains 1 and 2 together actually. And after that, we are in 1 and 2. Here, if we actually see A, we can stay at 1 and actually go to 2. And if we see a B, we have again 2 options. We can go to a state number 2 or back to a state number 1. So here, this is the transition function for this state. And as you can see here, because this state contains 1 and we know that 1 is our active state, so this state here is also one of our accepted state that we have. And again, if we are in 1 and we see a B, actually we can go to a state with only 2 in it. So it will become like this. And after that, if we see a, because we know that when we are in a state number 2, actually when we are here, we don't have any transition function for alphabet that is equivalent to a. So we don't have any options. So we must add a new state here with a on it, and this state is our reject state that we will show it like this. Because in this state we can't accept anything, and actually there is no transition function for this state, so it will become like this. And yes, oh, I forget something here. When we are in a state 2, if we see a B here like this, we must back to our state number 1, so it will become like this. Yes, this is the equivalence DFA for first part that we have here. This is for part A, and now let's go for part B. In the part B, we have a NFA that contains 3 states here, 1, 2, and 3. So based on the theorem, our equivalence DFA must have 2 to the power of 3 states on it. So it will become like this, 2 to the power of 3, that's contain 8 states because our k is equal to 3. This is not the number of our states in our NFA. So let's start to draw the actually equivalence DFA here. Based on this NFA that we have, we must start with 1. In the first state, we are in 1, and also we have this epsilon transition here that with any input we can go to a state number 2. So here we must have this state as our first and start state, so it will become like this. Actually, like this contains 1 and 2, because when we start our NFA, we can stay in 1, and or actually if we use from epsilon transition, we can go forward and go to next state that is equal to 2. So this is our first state, and after that we must check some things. And also we know that the state number 2 is our actually accept state. So this state that's contained 2 will become our accept state here. So after this state here, if we see a, we know that if we are in 1 with a, we can go to a state number 3 based on this transition here. And if we are in actually 2 here, we can start with 1 and using from epsilon transition here, and after that use from actually a like this and back to our first state, and also we can use from only the transition function and go to a state number 2. So here if we see a, we have to go to this state actually like this. It will contain 1, 2, and 3, and because it's contained 2, this is one of our accept states, so it will become like this. Yes. And after that, in this state, if we see an a, we have to stay in this state here actually, so it will become like this. Yes. And after that, for the first state that's contained 1 and 2, if we see a b, for 1 we don't have any transition function with b, but if we use from this actually epsilon transition here, we can go to state number 2, and after that again we don't have any transition function for the letter b. So for transition function with b letter, we don't have any state, or better I say, we don't have any transition that's contained b on it for state 1 and 2. So we have to go to the actually empty state somehow, or reject state. So it will become like this. actually, yes, with B actually. And we know that when we are in this state, we can't actually escape from this state. So with any alphabet on this state, we will stay here. So it contains A and B like this. Yes, this is good. And here we have this state 1, 2, and 3. Let's test B. When we are in 1, 2, and 3, if we are in 1, we don't have any transition function for B, and we know that for 2 we don't have any transition function for B. But if we are in this state here, 3, if we see a B here, actually we have two options. We can stay in our state or go to the next state that is equal to number 2. So based on this actually transition here, we have this state here that's contained 2 and 3 like this. Yes, and because it's contained number 2, this is one of our active states, so it will become like this. And yes, this is so good. Let me fix this. Yes, and after that, in this state that's contained 2 and 3, if we see an A here, if we are in the state number 3, we can go to the next state that is equal to 2. And after that, actually if we are in a state actually number 2 and we see an A, we have two options. Actually, we can go to the next state that is number 1 here like this, and after that we can use it and back to the state number 2, but until this part we have the state number 2 in our state. So the final state will become like this. Actually, let me show you. We have only actually 1 and actually 2 in our state, so we must back to our first state here. We have it until this part, so we have this transition here. It will become like this. Yes, and after that, when we are in this state, if we see a B, actually if we see a B in this state here 2 and 3, for 3 we have two actually options. We can stay in 3 or go to the next state that is B, that is 2 actually. And we know that when we are in state number 2, we don't have any transition function for letter B, so actually somehow it will become equivalent to this here, actually like this. And after that, if we want to add other states to this DFA that we have here, let me say you one note that you can remember. Here we test all of the states that we can actually make sure to go to them with actually different transition function that we use here. But there is one note that I want to say too. And we know that based on this theorem, we must have 8 states for our equivalence DFA. But there are some states that don't have any actually, we don't have any input transition to them. For example, for a state that's contained 1 and 3 together, for this state here, we know that, let me first check this one here. If we are in actually state number 1 here, and we use from A transition, we can go to the next state that is equal to 3. And if we are in the state number 3, we can use from this state here and go to the next state that is equal to 2. And if we are in this state that is equal to 2, we can use from this transition here and go to the next state that is equal to 1. But actually notice that there isn't any state that we can use it to go to this state here that's only contained 1 and 3. So actually there is a mistake here, and actually this is not a mistake. This is somehow an optimized solution, because there are some states that you can't reach them with any transition. So actually you can't skip them and don't write them in your equivalence DFA. So based on this, our equivalence DFA only have 4 states here. And if I want to actually complete this equivalence DFA here, I must add 4 states. That one of them is 1 and 3 here. Let me show you 1 and 3 states. That we know that when we are in 1 and 3, if we see a, we can go to a state 3 based on this transition. And if we are in 3 and if we see a, we can go to the actually a state number 2 with this transition here. So for a transition, we have this arrow. And if we are in 1, and because we don't have any transition for letter B, we have to skip it. And if we are in 3 and see another transition here, we have 2 options. We can stay in a state 3 or go to the next state that is equal to 2 based on this transition. So it will become like this actually. We will back to the state that's contain 2 and 3 both together. And because there isn't any input arrow to this state here like this, we can actually somehow erase this state, because there isn't any option that you can reach this state here. But we want to actually draw the complete equivalence DFA here. And actually we have 3 more states to draw here that are 1, 2, and 3. For state number, actually, let me tell you 1. For state 1, it will become like this, yes. If we are in state number 1, we don't have any transition function for B, so we must go to this empty state here. But if we see an A, we can go to a state number 3 with this transition function here. So we must add some new state here that's only contain 3 with A like this. And after that, we are in a state number 3. If we see a B, we have 2 options. We can go to actually a state number 2 with this transition here, or we can stay in this state using this transition here. So we have this arrow for a state number 3 like this. And if we only use from the transition with letter A, we have to go to the next state that is equal to number 2. So we must add this new state here like this. That's only contain 2 on it. So it will become like this actually. And after that, we are in state number 2. In number 2, if we see actually an A, we have to go to the next state that is equal to 1. And after that, we can use from epsilon transition to come back to the state number 2. So we must actually add this transition here with A like this. And we know that we don't have any transition function for letter B if we are in a state number 2. So we must add this actually transition here with B. And if you notice here, all of this state 2, let me show you actually with another color. This state 2 and 3 and 1. And actually this state here. The state that's contain 1 and 3 don't have any transition function that we can use it to actually enter this state. So we must actually delete this state here. And for a state that's only contained 1, we don't have any transition to enter this state here. So we have to actually delete this state here. And if we delete this state, after that, we don't have any transition function to enter actually a state 3. So we have to delete this state. And after that, if we delete this state, we don't have any transition function to enter the state number 2, because we must delete this transition here. So after that, we also need to delete the state that's only contain number 2. So in the final and actually somehow optimized DFA for this NFA here, we only need 4 states. That's one of them is 1 and 2. We have 1 and 2 and 3 and 2 and 3, and we only need the empty set here. And yes, that was the solution for actually question number 16 from Sipser textbook. I know that this question may look so hard, because actually this theorem that we use here, in the first look it looks so hard. You must actually solve a lot of examples from this theorem here, and if you keep practice and practice and practice, you will become expert in this issue, and surely you can solve any question that you see about this issue here in your exam. And yes, I hope you guys enjoyed this video and actually learned a lot of useful things for your exam, I don't know, for your interview, and or a lot of things. And if you have any idea or opinion, you can leave them in the comment part. And if you like this video, you can like it and subscribe to my channel. And also I have a GitHub actually profile that you can check it. I will upload all of my solution in there. Solution for coding interview, this solution here that contains Sipser textbook and CLR's textbook. And yes, you can check it. And yes, that's it. Have a nice day, guys. Goodbye.